Okay, thank you for introduction. Hello everyone. I'm Hong-Suk Lee from Neurocle, and today I'm going to talk about how to maximize your inspection accuracy with deep learning. So I have like the four parts. Firstly, I'm going to talk about like synthetic defect data, and secondly, I'm going to talk about anomaly models. Third, our unique models, which is a patch classification, and lastly, I'm going to talk about like auto deep learning algorithm. So before we start, let me give you one question. Like, what do you think of the end of goal of the deep learning vision inspection? We have to think about why we are using deep learning. It's very simple, actually. Why we are using deep learning? Because we want to maximize the deep learning inspection accuracy. If we can maximize the accuracy with the conventional one, we are going to go for it. But there are so many irregular defects, so that's why we are applying deep learning to maximize the accuracy. However, try to maximize accuracy. There are some challenges we confront. Maybe we can categorize in three things. The first one is data scarcity. So normally we can easily gather OK data from the manufacturing lines, but it's very difficult to gather some defect data. So we have to solve this problem when we're applying deep learning, because deep learning is basically learning-based algorithm. And secondly, there are some data imbalance of each classes. Because, for example, you have like 5 different types of a defect, maybe 1 or 2 types of defect you can easily gather, but others, it rarely happen. In that case, we also think about how to solve these problems. And lastly, nowadays, we try to have very new application with high resolution images. In that case, we have to think about how to minimize how can I say, missing information in this high resolution data. That's because deep learning, when we train the model, we cannot use so big image data. Sometimes we have to resize, sometimes we make patches, but we have to think about how to solve this problem. So for that, I'm going to introduce 3 things. Try to solve the data scarcity, I'm going to introduce synthetic data methodologies. Secondly, I'll try to make some data imbalance better. I'm going to introduce anomaly models. And lastly, try to deal with high resolution data. I'm going to introduce patch classification model. Let's go to the first topic, synthetic data, to solve the data scarcity problems. So as I mentioned, in the manufacturing side, we are lacking of the defect data. So this is a big problem. So try to solve this problem. We introduced the GAN model, generative adversarial network. So in GAN model, actually, we have two models. One is the generator, and the other is the discriminator. So generators will create new images. Actually, here, we compare with some like the police and some, how can I say, counterfeit money criminals. But generators will generate the new data, and the discriminator will discriminate whether this is the real or whether this is a fake. So compared with these two networks, the GAN model can create a very accurate, very suitable image data based on your defect types. So this is how you use a GAN. Of course, we have to teach the defect types, defect shapes, so that we need at least 10 defect data, and then teach training the GAN model. And then after you train the GAN model, you're going to use the OK data. And then based on the OK data, you're going to put these defect stamps on the surfaces. And then GAN model will generate artificial defects, synthetic data like this. This is the basic concept of the generative adversarial network. And of course, GAN model, we have 2 networks inside, as I mentioned, discriminator and generator, so that GAN model is actually a little bit a heavier model compared to the other normal models, because it includes 2 models at the same time. So that means actually it's also difficult to handle high resolution data. So we have a patch mode of a GAN model to train and to create the very small defects on the high resolution images. And also, as I mentioned, we only need 10 defect data for the training, so it's very practical to use on the manufacturing side. And also, we provide the stamps, defect stamps, when you create new artificial defects based on the OK data. Because we train like the 10 defect data, but when you generate the images, if you put some little bit strange labels on the OK data, then maybe your GAN model's performance can decrease. So that's why we provide defect sample to make the multiple synthetic data very well. Yeah, so you're gonna put these stems on the OK data, and you can easily create. So we have many use cases. For example, like this is an example of the inspecting batteries. So batteries, sometimes it's difficult to gather some defect data, so that's why we use GAN. So before we use GAN, the accuracy is around like the 87%. But by using GAN model, we generate like 40 defects about the foreign substance and 80 defects of the dent images, and then the accuracy goes up to around like 97%, which is higher, 11% higher than a previous result. So this is one of the advantage of the GAN model when you're having a hard time gathering some defect data. Let me go to the second topic, which is anomaly models. If you have some class imbalance among your defect types, this is also a problem. As I mentioned, maybe defect 1 and defect 2 you can easily gather. You have maybe like the several hundreds of the defects for the first and second defects. But maybe for the defect 3 and defect 4, you only have 1 image or 2 images. If you train these trained data, then there's high possibility that the model can detect only defect 1 and defect 2, and it cannot detect defect 3 and defect 4 because of this class imbalance. In that case, we recommend to use these anomaly models, because nowadays we have to detect this irregular defect type. That means defect types is getting number of the defect types is getting larger and larger. So that's why we are thinking of using this unsupervised learning, which we can call the anomaly models, because in this case we only train the normal data. We only train the normal data. That means the models will learn what the boundary of the normal data is, and then we can easily find out abnormal cases without any big amount of the each defect types. Yeah, so we provide 2 types of different anomaly models. One is anomaly classification, and the other is anomaly segmentation. The result is very similar like the normal classification and normal segmentation. So classification, as you can see, we provide a heat map, and then for anomaly segmentation, we provide some blobs on the surfaces. So as I mentioned, the biggest benefit of this anomaly model is we can train when the defect data is very insufficient. And also, we can minimize the resources for the model training and model image labeling. Normally, we only train the normal data. That means actually training process is much simpler than the normal training, so that we can minimize the training time. And as well as we don't use the defect data for training. That means you don't have to label one by one for the defects. So this is another benefit of the anomaly models. So there are also many use cases, but one use case is finding some missing palette on the logistics. So in that case, 5 pallets should be placed in each section, but normally it does. But sometimes actually there are only 4 pallets. In that case, we can use this anomaly to find out some missing pallets. So yeah, because in this time, it's really difficult to find some defect data, so that's why the accuracy of the normal classification was really low. But anomaly can solve these problems. Yeah, I'm out of time, so I should go faster. So maybe the next one is the patch classification to overcome the limitation of the previous classification model. And as I mentioned, these days, we are using very high resolution data. For example, we use many line scan camera. In that case, the resolution is really, really big. But the problem is computation power is not that big. We normally, when you're using classification model, maybe we have to resize the data into 1024 by 1024 or 2048 by 2048. But that means if your original data is larger than like the 10K, that means you have to resize at least like 5 times or 10 times. But if the defect is large enough, that's okay. But if the defect is very small in this high resolution data, then it may cause some problems. That means the models cannot detect those defects. So we want to solve this problem. So maybe we can think of, okay, I have a classification model. Maybe I can just divide the original images into this kind of like the patches. It works. Sometimes it works, but if the defects are large enough, then actually defects will be divided into different patches. That means if you just divide these patches, actually you cannot meet your highest accuracy because there will be some missing information between the borderlines. So that's why we invented this patch classification. Of course, we divide patch by patch, but of course, there's some algorithm. We make a balance between all the borderlines. So you don't have to worry about any information missing between the borderlines. You can just draw the labelings like this with the patches. Then our patch classification model will train it and then find out the defects on the high resolution data. The first one, you can click it for labeling. You can drag, or you can also make a batch labeling for each patches. This is what we provide for labeling for patch classification. So another benefit of the patch classification is very easy to integrate, because if you just divide the patches by yourself, you have to think about the pre-processing and post-processing of the classification model, and it takes some time, and then sometimes it makes some error because it's not easy. But we have our total pure model of the patch classification. That means you can just import your images into our model. Then our model will predict. Our model will make all the patches into the original data, then get the result. So it's also very easy to integrate into your system. So we have many cases of this patch classification, and one use case is the wire defects. In this case, we have to detect very small wire defects, so that we are using line scan camera to get some high resolution data, so that we cannot use the classification model, and then it's a wire, so that we also cannot use a segmentation model as well. So we need a classification, but we cannot resize a lot. So that's why we apply the patch classification, and then we can reach higher, up to 98% of the accuracy compared to the normal classification, which is 66% of the accuracy. So this is another one example of the patch classification. So I just introduced 3 things: a GAN model to create some artificial defects, an anomaly model to solve some problem with the class imbalance, data imbalance, and lastly, patch classification to deal with the high resolution data to apply the deep learning. And then all these techniques are included in our auto deep learning vision software. We have a training software called NeuroT. This is like the T stands for the training, so that NeuroT is covering from the data acquisition to the model creation. And then once you create your model, you can apply our model with a runtime library, which is called NeuroR. The biggest benefit of these things is actually we have an auto deep learning algorithm which optimize deep learning architectures and hyperparameters automatically, so that if you're not a deep learning expert, you can easily create the best performing deep learning model with just one click. So when we train the model, we're going to optimize our model based on your training data, and all your deep learning architectures and hyperparameters will be optimized automatically. And besides auto deep learning, we have many good cases, many good features, as I explained today: GAN model, patch classification, and anomaly classification, and anomaly segmentation. So these are the kind of the new technology we show to this exhibition today. So if you want to see more details, please visit our booth at Hall 8 and 8B11. It's right in front of the entrance of the Hall 8, right over there. Thank you very much for my presentation. Thank you.